Hi guys, and what do you think is today? Design time again. But today I will revisit an older project, a real old project. It was, I think, my fourth video or something like that. It's a couple of years ago. It is an design I made to help me calculate or determine the resonant frequency of Tesla coils. I'm doing a lot of things with Tesla coils and power electronics, and many times I want to know what the resonant frequency of the coil that I calculated and that I wound is at the moment in reality. There are quite many options you can do that. You can calculate it, you can use a grid deep meter eventually, like the one I showed a couple of videos before. But you know me, I want to over-engineer things and make things more technical. Or what you see here, at least for the Tesla coil, it can be done easier too, but I like to make my life easier. So, what does this thing do? I'm using an AD9833, that's a DDS chip from Analog Devices that can produce square wave, sine wave, and triangle waves from frequencies, I don't know, lower than 1 hertz up to over 10 megahertz or 11 megahertz, something like that. It is quite easy to use. Additionally to that, this is the heart of the whole system. I'm using this for this project as a poor man's generator. Let's show DDS generator that you can use. The output can be taken from here. And of course, as the primary reason, the DDS resonant frequency counter, or to find out the resonant frequency anyway. First of all, how does that work? It generates a frequency that is selected by these two rotary encoders, as you can see, we will see later. This square, I'm using a square wave for that because it has the highest amplitude. The square wave is then level shifted from 0 to 5 volt to 0 to 12 volts with a dedicated level shifter IC and driver. We will see that again on the back. The whole thing is powered with a wall-wart PSU, 12 volt PSU. This generated frequency is then coupled via a capacitor to one of these coils, for example. That's a smaller Tesla coil. Additionally, there is an IC, there is an LED and an optocoupler on the back. Both the LED of the optocoupler and the viewable LED are connected anti-parallel. What happens when the frequency selected here matches the resonant frequency of, again, one of these coils? This LED will have it will be maximum illuminated. So the current through this LED will be at this maximum. And because of after the capacitor and the combination of the Tesla coil acts like a low-pass filter. That means you will have a sine wave, more or less. A sine wave current. That means again that not only the optocoupler will see one half of the sine, the LED will see the other half of the sine. So if this gets high, the other thing gets high, and the opposite, it is inverted. But this is enough to show me the relative strength or relative current that this resonant reaches. Further, from the optocoupler, the optocoupler is connected to a microcontroller that shows the same strength, resonance strength, let's say so, as a bar graph. Okay, this is more or less the functionality of that. The second thing is you can, if you compile the software and you use a conditional compile switch that I've put inside, that I'm using, you can use this thing also as a poor man's DDS frequency generator. This is how it looks from the back. You will say, why on the earth are you using modules to make this thing so big? Well, big, it's a 10 by 10 PCB port. Here you can have a more detailed view. Let's zoom maximum. You see the module for the AD9833. You see the microcontroller unit. It's just an Arduino Nano. I will explain in a jiffy why I'm using what I'm using. And here you see an I2C to parallel LCD converter module. The rest is done with a mix of through-hole components like the capacitors, and SMD like pure resistors, the optocoupler, the coupling capacitors, and the level shifter IC. The level shifter IC is a quite clever one because it gives you a lot of power on the output if you parallel the gates. It's a 4504. It's quite an old IC, but it does the job. So why I'm using these modules? First, number one, this thing is not intended to be in production. It's just an hobby project, not hobby project. It's a project that I made for me and perhaps for a few friends or a few viewers. That's it. But never intended to go to production. If it would be something that it will go to a production, I would give a lot more care on the design, and all of it will be on one PCB without modules. Second reason is that the sum of the parts that I would need to make these modules, because below that you have the USB chips for the Arduino too, would be cost me more than twice of the price of these three modules. A lot more than twice. These are cheap modules. This thing costs, the Arduino costs $1, $2. So doesn't make really sense. The third reason is, again, if somebody wants to replicate this design and to build one for his own, to make it easier for him. It should be an easy project. It just should be a tool for Teslacoil enthusiasts or something like that. And the fourth reason is because I'm lazy. I have to solder a lot less, and the layout is much easier. But okay, I made this fourth up, of course, as you know, of course. Anyway, this is how it looks. CPU unit, more than enough for everything that I want to do with that. The DDS itself, and this converter is so I can use an Atmega library or Arduino library. It's called Liquid Crystal I2C or I2C Liquid Crystal, something like that. It's nothing else it's nothing more that you can use the 8844 commands for the parallel displays, but using this controller through I2C. So it's a difference if you to have, I don't know, 8 lines to use for the I2C, and now we have only 4, where 2 of them is, one of them is ground and the other one is 5 volts. It's a nice adapter, converter, and it's clever. I don't know, I think Intel was, this was designed, it was shown for the first time in an Intel application note, and the Chinese just took it and made the modules, but very good idea. The trim pot is for adjusting the contrast of the LCD. Here you have the main chip. It's quite an old one. It's a PCF 8574. It is an GPIO or IO replicator. GPIO replicator. That means you can control the chip through I2C. There's a sister chip for P2, and it gives you a lot more pins, IO pins. That's all. This is how it works to get the commands through the serial I2C and set the correct pins that are needed for the parallel LCDs. So it has, as I said, contrast. It has the possibility to completely disable the backlight of the LCD. The backlight is again controlled via a GPIO of this chip, or completely disabled through this jumper. The interface itself has even the possibility to set the address. For now, I think it's 26 or something like that. But if you use more of these displays or more of these adapters, you can set the address, the I2C address. I used here as few as possible SMD and easy ones. Of course, one of the further reasons that I'm doing this video is because I made some updates to can use it even more as a DDS, as a low-cost DDS generator. And I'll show you what I did after that in the design in a 3D board view. From the front side, I'm using a 1604 type LCD. Here you can see the pinout, the pins, which I used, and the function of the pins. This is a standard legacy LCD that you can find everywhere, AliExpress, eBay, whatever you want. It is a 4 lines by 16 rows characters. This one has a blue background, a blue background with a white font. It's quite big, as you can see here. It takes most of the real estate of the front of the PCB itself. I'm using two rotary encoders. One is for the stepping, the multiplier, the frequency multiplier for 1, 10, 50, some blah blah, etc. The step is controlled through the rotation, via the rotation. Then you have the frequency, up and down through the rotation, and the press, the button, is for setting the output, enable or disable. Further, the step one, if you keep it pressed, it makes just a reset. I don't know. It was just fun to have some function for that too. In a DDS mode, this one, the step, I think, will change the output wave from sine, triangle, or square. And this again, the push button is only for output enable, disable. The BNC connector can be used, is used as for the output of the DDS when this thing is in the DDS generator mode, or to connect a frequency counter, an optional frequency counter if you want, when it is in the Tesla Resonant meter mode, like that. Very important is if you use it in the Tesla resonance meter mode, to connect the earth terminal to mains earth. Because why? How this will work? If you have, for example, this coil here, and you connect it directly to the output of the resonance meter, you will say, how do you measure a resonance without a capacitor? Well, the capacitor is, let me call it an air capacitor. It's a capacitor that is between this point here, through the air, to the mains earth. That means everything that interferes between this space changes the capacity. Even my hand, everything, you will see that later. This is very important because if you want to know just the resonance of the coil, keep your fingers and hands away and everything else, and put this as far away as possible. Okay, this is, I think, enough now for theory. Let me show you how it works. Okay, this was quite difficult to bring everything, the coil and the meter, in focus, or to bring it to is readable more or less, yeah? As you can see here, I have set the frequency of 677 kilohertz. This is not the resonant frequency of the coil. I like it much more like that. This is the resonant frequency of the coil in combination with my hand that holds a neon bulb. This one. Whoa, that looks spooky, like an alien. So let's find out now the resonant frequency of the coil itself. Oop, this is the multiplier by 10,000, and now the frequency. Let's go a little bit down. That's too high. As you can see, at the frequency of 767, we have a little bit like that. Problem is, if I do it like that, you cannot see the display. Anyway, you see what I mean. Stay here, and let's turn the multiplier down to 1000. Let's go a little bit lower, even of 100. So this is more or less maximum. So something, if I go a little bit further away, $770 something. You see how sensitive the whole thing is. When I put my hand near the coil itself, it changes completely the resonant characteristics. This is what I mean, as far away as possible. And I will put it even more far away to see what happens now if it is not that sensitive anymore. Yeah, that's better. That's better. Now I'm quite far away. Problem is, now you don't see the coil, but I will do like that. And look what happens. You see the LED, you still see it. Yep. If I put the coil at the moment here is absolutely not in the maximum resonance. I have to go so. Now I set the resonant frequency to 663 kilohertz, 600 hertz. And theoretically, this should be the resonant frequency of the combination of the coil itself, my hand, and me holding the neon bulb, you see? Every time I go near and the neon bulb lights, the LED is getting stronger. Because at this time, this whole caboodle here reaches the resonant frequency. This is how it looks. And just for fun, I will show you the results of a much larger coil. So, this is a much larger coil, as you can see. Look at it, baby. Look, look, look. And this is the output. I had to put it much farther away because the sensitivity is much higher. Look at that. Look at the energy that this thing emits. And the same here. not even touching it. When I do that, this happens. So, I know, it's a toy, but it can be very helpful if you're using, if you're playing with Tesla coils and high energy coils to at least find the ballpark of the resonant frequency. For example, I have this one too. Wait, I have to get it back. This one too. This one came from, it came with a Tesla coil, a Class D Tesla coil from Russia. It has a lot less turns, and it resonates to 1.4, 1.5 megahertz, yeah, for example. But something else I wanted to show you is that you cannot use only this larger display, that is a 1604. You can use these ones too, the EA series dock displays, where I made the adapter that I showed a couple of videos ago. Not many people were interested in that video, but anyway, perhaps somebody is interested, and then he can build it if he wants, because for all of that, the schematics, the design files, and the code are available on request. But now, the most important, guys, if you like my videos, if you like what you see, if you want to see more of this kind of stuff and a lot of other interesting things, please press the like button, subscribe to my channel, and ring the bell. Push the bell button so you get a notification when a new video comes up. All this will help my channel to grow and to give you more videos. So now let me show you in a 3D view what I changed, because this is an update video too. The larger changes, the major changes have been made to make this thing a little bit more usable as a DDS. That means I changed a little bit the layout, I changed the software a little bit, and I changed the output. The output now is you can attenuate the output on a software basis. And why? Because in sine mode and triangle mode, it outputs the DDS gives you a 600 millivolt peak to peak. And if you put it on square, you have 5 volts peak to peak. So that's not very useful, or it is in many occasions. This was the reason that I added an attenuation circuit, an optional attenuation circuit that is triggered by software, if you want it or not. I added additional buffer op-amp, a high-speed buffer op-amp with a 50 ohm output. And on the back, let me disconnect all these things. Here you see the earth connection here that goes to the mains earth. Let's turn it off. On the back, you will have a switch that can switch between DDS and Tesla resonance meter on the fly. The software will be like that. It will in all half a second or a second will check where the switch position is and set the correct mode. So let me show you the 3D board view. Okay, here we have the new layout. This is the circuitry added for the attenuator and the buffer. Of course, the writing the layout changed a little bit too. And this is the back where you can see the switch itself. So the whole idea was to make it as easy as possible for people that want to replicate and build themselves one. Now I will show you the data sheets. This is the voltage level shifter, what I'm using, that with the paralleled gates I'm using is quite potent to drive even these bigger coils that I showed you. And a little bit of a little information on the DDS, the AD9833. So that's it for today. I hope this additional information, this additional details are interesting for you, for anybody that wants to build this project. I made it as easy as possible, as I said, with modules. Again, the design files and everything, the code, everything needed is available on request. Thanks for watching, guys. Bye. Cheers.